Alright, and now for the fifth one, we have that a hollow chocolate box is manufactured in the form of a right prism, ooh, buzzword, with a regular, big buzzword, hexagonal base. The height of the prism is h centimeters, and the top of the base and base of the prism have sides of length of x centimeters. So we have the h height here, and the x's are there. So here, here, and technically also here, 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 and here. Let's not forget the bottom. See, so all of those that I just put in blue are gonna be x. Okay. Cool. So for part A, they tell us that given that sine 60 equals square root of 3 divided by 2, show that the area of the base of the box is equal to that. All right, so whenever you have a show that, okay, really, you just have to find the area of the base. Okay, like, I know that they use the word show, but just find the area of the base. Okay, and once you find the area of the base, your work, right, your procedure is how you show it. All right. And so really, you need to find the area of the base, and they give you a hint. And so the hint is sine 60 equals the square root of 3 divided by 2. So let's see what we can do. The buzzwords here, as I mentioned earlier, are regular hexagonal, right? And so a regular shape, any regular shape, is going to have all of its equal, a lot of equal sides. See, so everything that I just put in blue is kind of like what makes it a regular hexagonal base in the first place. Because this could be a hexagonal shape, but all of its sides could be, not the same, right? So in this case, they are all the same. That's what makes it regular, and that is already a big hint. It's a big hint because that actually allows me to do the following. Notice what I'm going to do up top, okay? Because all the sides are the same, I can actually go like this. Boom, 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 bada bim, bada bam. So now all of these are x, quite literally. All of these homies are x. And not only are all of these homies, all of these sides x, we also have 6 because we have 1, 2, 3, 4, 5, 6 triangles, and they are all what we call equilateral. They all have the same side, which means that they all have the same angle. And how much is this angle? Well, if they're all the same angle, and I have 180 degrees inside a triangle, take 180 divided by 3, I get 60. So each of these sides is actually 60. All right, so that right there is massive progress. So now the area of the base, right, which is this whole guy here, we just identified is actually just 6 triangles, and those 6 triangles are all equilateral. And so if I find the area of one of these triangles and multiply it by 6, I get the whole thing. See, so I find the area of one of them, multiply by 6, we're good to go. So what is the area of one of them? Well, how do you find the area of a triangle? You have two options. Area of a triangle in your formula book sheet has the classic, which is base times height divided by 2. And the other one, more new probably, is trigonometric. See, you have 1/2 equals, area equals 1/2 times a times b times sine c. So this is where I'm getting my formula, just so that we're on the same page. That it? So for your formula book, the area is going to be 1/2 times a times b times sine big C. Now, if you've seen some of my other videos, you know what little a and big A, little b, big B, and little c, big C are. Okay, but just as a very quick recap for anyone watching this, whatever, for the first time or anything, if I have this triangle, all right, the angle inside, for example, here is going to be a big letter. So this could be angle A, which has side little a. This could be angle B, which has side little b. These can be angle C, which has side little c. So the big letters are angles, the little letters are sides. So if I apply, okay, this same formula from here, the area of one triangle, it's going to be 1/2 times x, which is a, times b, which is going to be another x, times sine c, the angle in between, is just going to be sine 60. And since I know that they told me earlier that sine 60 is this guy here, I suddenly have 1/2 times x squared, because x times x, times square root of 3 divided by 2. If you want to get fancy and combine terms or whatever, you actually end up with x squared times square root of 3 divided by 4, because we have 2 times 2 on the bottom. See? Awesome. And from this step forward, since this is the area of one triangle and I want to find the area of the whole base, I take this guy, multiply by 6, right? And so I have 6 times x squared, square root of 3 divided by 4. I simplify the 6 and the 4, so I divide both of them by 2. So this goes to 3, this goes to 2. I end up with 3 x squared square root of 3 divided by 2. So this would be the area of what I'm going to draw now in yellow. The area of all of that is going to be this, which is part A. Alright, and for part B, we have that given that the total external surface area of the box is 1,200 centimeters squared, show that the volume of the box may be expressed as blah. So we have surface area and volume. Those are the two things that we're working on. We probably have to use both. Alright. So let's go up here and let's do the surface area version and the volume version and see what happens. Alright. So surface area of this figure, there is usually not really like a formula for like the surface area of an entire sort of like object or shape or whatever. But you do have surface area for many other things in your formula booklet. So over here, for example, if I go to surface area or surface in general, we have curved surface area of a cone, of a sphere, of a cylinder, and also area in general, which can help for surface as well. Parallelogram, triangle, trapezoid, circle, etc. See, so very general stuff. Not quite what we're going for. And so for surface areas, many times you kind of have to eyeball it. See, so in this case, we have two regular hexagonal bases. See, so I have the one up top and I have the one down in the bottom. So I'm going to write that right now. Surface area equals 2 of the hexagon thingies. Plus all of these guys that are going down the middle, ¿cierto? Which are 6 rectangles. So this guy here, 1, 2, 3, 4, 5, 6. I also have those 6 rectangles. See? So I also have 6 rectangles. So I'm going to plug in on the left side what we have. So surface area, we were told actually from part B that it is 1,200. See? So here we have 1,200 equals 2 times the hexagons. The hexagons are actually what we had in yellow this whole time. So we have 3x squared, square root of 3 divided by 2, plus 6 of these rectangles. And now the rectangle, what is the area of that? Well, whoops, we have height and the side down here, x. See? So we're going to put 6 xh, right? Straight from the diagram, there it is. Perfect. So now if I go ahead and sort of work around with this, I end up with 1,200 equals 3x squared, square root of 3, because this 2 and this 2 goes away, plus 6xh. Alright, so that is for surface area. And now for volume, okay, if we go ahead and work with volume for now, what the hell is the volume of this? Well, we go to our formula booklet, search volume, see what we find. So for volume, we have whatever that is, of a cuboid, of a cylinder, of a prism. See, and so for volume of a prism, we have big A and H, right? Where big A is the area of the cross section and H is the height. So H is the height, we have that, or I mean, not literally, but we know that it's H. And the cross section again makes reference to what's in yellow. Okay, it's basically the base of your prism. All right, the base of your prism is going to be the cross section. It's going to be big A. Right. So this whole guy in yellow is going to be big A. So volume in this case is big A times H. Big A we know is what we said was in yellow. So 3x squared, square root of 3 divided by 2 times H. So right now I have two equations, right? I have the volume one, I have the surface area one. I have two equations and two variables, see, x and h. So essentially, if I have h in terms of x, which would be the same as having h equals something something x, I can plug that in over here, and I end up with just x. So our main goal right now is that I go from 2 equations to just 1 and having just one variable instead of 2. So we're going to have h equals something, right? Why do we want h equals something? Because the formula for my volume over here has only x. It has only x, so that is what I want to reach. Only x, get rid of your h. So for this guy on the left, the surface area, I'm going to have h equals something, all right? So for getting h alone here, I first need to start off by subtracting 3x squared and square root of 3 to both sides. So that makes this go away over here. 1200 minus 3x squared square root of 3 equals 6xh. I still need to get h alone. What is it being affected by? By a 6 and by an h, it's being multiplied. So I do the inverse, divide. So divide both sides by 6x. I go like that. See? So 1200 minus 3x squared square root of 3 divided by 6x equals h. If I want to keep on simplifying, well, first of all, I'm going to put h on the other side because I'm picky. But also, I can split this fraction in 2, actually. And I end up with 1200 divided by 6x minus 3x squared square root of 3 6x. So I split it in 2 just because visually it's more appealing, but also for simplifying, I find that it's easier. And so on the left side, I'm going to end up with 1200 divided by 6, 200. So 200 divided by x. And for this other guy, I end up with just 1x on top, square root of 3 divided by 2. If anyone's confused what happens to the x's in that case, if I have x times x divided by x, I get rid of 1 on top, 1 on the bottom, I end up with just x. See? This is no different, the scenario that I just showed, to this. It's literally the same. In fact, this is the same as this, is the same as this. Because I get rid of this guy and this guy, you end up with 2x on top. See? Alright, that was like a mini session on exponents, and you know, we have x's like that. See? Alright, anyways, this is my h. Alright, so as I said, now that we have the height, we're gonna go ahead and plug it into the volume. So volume equals, well, the same thing I had before, 3x squared times square root of 3 divided by 2 times h. So all of what I'm plugging in now is h, this guy here, see? It's gonna be 200 divided by x minus x square root of 3 divided by 2. Alright, so that right there is h. See? All of this. So since we're multiplying these two terms, right, I can go ahead and distribute. So this times this, and this times this. For the first guy, I end up with 3 times 200, that's 600. So 600 x squared square root of 3 divided by 2x. And for the other term, I end up with 3x cubed, because I have x squared times x, times square root of 3 times square root of 3 divided by 2 times 2, 4. All right, so let's take a moment and simplify some of these terms let's take a moment and simplify some of these terms. 600 divided by 2 is just going to be 300. The x squared on top of interacting with the x on the bottom, as I mentioned earlier, is just going to be x and square root of 3. So that is with the term on the left. And for the term on the right, I end up with 3 times x cubed times 3, because these two guys combine. See, I end up with inside square root of 3 times square root of 3. I end up with square root of 9. Square root of 9 equals 3. Right? So those two guys actually combine. That is how square roots interact. So that is why I ended up with times 3 over here, divided by 4. See? And since I have times 3 times 3, as I'm putting in red, that actually just turns into 9 over here. All right. So that is it for the term on the left. This is for the term on the right. This is what I got for volume. I compared to what I had earlier, or to what I had to show, sorry. We have that volume equals 300 times 3 times x, times square root of 3 times x. This is practically the same, just this is flipped around, it doesn't really matter. Minus 9 divided by 4, x cubed. 9 divided by 4 times x cubed. Awesome. So that is how you show for part B. It's very important that you notice that you have volume and surface area going on. of course, you need to combine them in some way. And the biggest hint for which that way should be is that originally I faced the problem that I have x and h as variables. Down here, as the final answer, there is no h, we have only x. So that is like my compass, that is my north. Make sure you end up with only x's, see? And so if you just try to do that, eventually you will find, or you will arrive to the answer. So that is for part B. Alright, then now for part C, we have that we need to sketch the graph of v equals blah blah blah. So my volume formula or function for x between 0 and 16. See? So whenever you're sketching a graph, it's very important to put key points. All right, so let's see how our graph looks like in the first place, and then we, well, highlight what we need to highlight. See? So I'm going to go to y equals, go ahead and graph it, and then sketch it onto my paper. Square root of 3 times x minus that fraction, which is 9 divided by 4. Right next to it, we have x to the power of 3. So I go ahead and open up my window immediately, and they already give me my domain, right? My values of x from 0 to 16. So I'm going to put minimum 0, maximum 16. And my y values, well, I can eyeball them later. But since we're talking about volume, I would assume it's kind of big. So I'm going to put minimum 0, maximum, I don't know, maybe 1,000. My scale for some reason is on 1,000. I'm going to change it to 10. To each their own. I go ahead and graph. All right, so clearly we can see that it goes up and then it goes down. So it probably looks something like this. It probably looks something that goes like that. Okay? So of course I can't sketch what I have right now. Like if I put this as my answer, it's terribly wrong. Okay? It's terribly wrong because you really, really, really want to show key points. The only key points you can show now is 0, 0, whenever it touches here, and nothing else. And showing the maximum value is always going to be important. See, so I want to make sure that I can show the maximum value. I'm going to keep playing around with my calculator for just a little bit more. I'm going to change my window again. Let's put 2000 just to make sure that we can see it. Graph. To my surprise, we still cannot see the maximum. But this third attempt might show to be promising. I'm going to go ahead and put 5000 because why not? All right. So I have a lot of that is additional. I'm going to change this just a little bit. Again, it's the IB. You just want to sketch it nicely if you can. All right, there it is. So my window right now is this is 0. This is 3,500. And this is 16. All right, so it's because you're sketching, you always want to highlight the key points. So as I said, the key points are going to be my maximum and where it touches here. Technically here it touches on 0, 0, so might as well write it down. Let's find out what my 0 is. So second calc, 0, left bound, right bound. So I'm going to do left bound over here, right bound all the way where I can't even see it, and I guess where my 0 is. Boom. So my 0 is going to be at 15.196, 0. And my maximum, more importantly, calc maximum, my left bound, I put it behind my maximum. My right bound over here. My guess somewhere near. There it is. So my maximum is going to be 8.77, if I remember correctly. 3, comma, 3,039. 0.34. Why not? All right, so that is good enough for sketching, honestly. Putting the scale also here is going to help. But for example, maybe putting the 8.773 here is not a bad idea. Got it? Maybe doing a dotted line, something like that can help. But what's going to net you the real points is going to be writing down the coordinates of key points, identify which ones they are as well. See? So in this case, it was the zeros and the maximums. Just like any parabola, really, let's be honest. So that is for part C for sketching. Next, we need to find the expression for that. Now, what the hell is that? Well, that makes reference to a derivative. So my volume equation formula thing, following from part B, we have 300 square root of 3 times x minus 9 over 4 x to the power of 3. Now at this level, at the IBAISL level, we will always do the exponent derivative. Okay, how do I know it's a derivative? Because of what's written here. See, when you put dv over dx, it's telling you do the derivative of your function v, so it's going to be this whole guy here, and respects to x, so only to that variable there. See? All right. So before we do the actual exercise, I'm going to first show a quick example. All right. If I have x squared, f of x squared, and I ask you to do the derivative of this, see? So d of f of x divided by dx. What happens intuitively is that this 2 is going to go in front, the x is going to stay there, and the exponent gets subtracted by 1. So 2x, 2 minus 1 is 1, same as just 2x. So again, the exponent goes down, you subtract the exponent by 1, and that's it. See? I know it's a little bit weird, but actually, derivative of an exponent is right here in your formula booklet. So if you ever forget it, you can check for it there. It looks a little weird because they put n in between and stuff like that, but it's no different. The exponent goes in the front, there's the n, and you subtract by 1. Bada bam, bada boom. So that is the derivative of x squared. See, that's what happens in this scenario. Let's see what happens when there's numbers in between. See, when there's numbers in between, by the most part, for now, you kind of don't give a shit. See, kind of. So in this case, we have the 300 with a square root of 3, which is next to the x. So this has to be multiplying, of course. The exponent up here is a 1. So I multiply by 1, and then I have x times x to the power of 0. Alright, I know that looks weird, but I'm going to leave it there like that for now. On the right side, I have 9 over 4 times 3, because the exponent of 3, times x, 3 minus 1. See? Alright. So that is like the first step. Now it's like seeing what happens to the numbers. See? On the left side, it's all going to stay the same, except for the x to the power of 0, which is actually just 1. So this is actually times 1 times 1. It's the same as if they just don't exist. Alright? For anyone that's confused about that, I'll show you a quick example. See? If I have 2 to the power of 3, that's 2 times 2 times 2, which is 8. 2 to the power of 2 is 2 times 2, which is 4. 2 to the power of 1 is just 2, which is 2. And 2 to the power of 0 is going to be 1. Why is it going to be 1? There's a couple ways of looking at it, and the one that's most intuitive to me is that if I go up like this, I am multiplying by 2. So 2 times 2 is 4, 4 times 2 is 8. That is how you go forward. See? If you go backwards, you divide by 2. So 8 divided by 2 is 4, 4 divided by 2 is 2, 2 divided by 2 is 1. Ta-da! That's why it's 1. See? Awesome. The same applies for, I don't know, 3 squared. 3 squared is 9, 3 to the power of 1 is 3, 3 to the power of 0 is 1, because you divide by 3 to go down. Anyways, that's a quick way to remember, or the explanation better said, of why anything to the power of 0 is always just going to equal 1. So back to the exercise at hand, the term on the left ends up like that. The term on the right ends up like this. 9 times 3 is going to be 27 divided by 4 times x, 3 minus 1, 2. So that is my trusty, rusty derivative in this scenario. And now for part E, we need to find the value of x which maximizes the volume of the box. Now actually, with how we approach the problem, we already did that from part C. We did that from part C by using our calculator. So actually, part E is already solved. If you want to show your work, you would have to say, I graphed with these values and I did calc max. And you're good. Like that's literally it. Say you're good. That would be part E. If you want to solve it like sort of like the classical way, or how it's intended to, quote unquote, even though both work and both are in the answer key, Because in part D we did the derivative, you can use the derivative to solve this. And so derivative, once you do the derivative of anything, you are now talking about slope, or rate of change. And so where your rate of change is equal to 0 is basically asking your function where, or when is my function, where does my function have a slope of 0? So having that concept in mind, here it's a slope of, I don't know, 3. Here it's a slope of, I don't know, 2. Here's a slope of 0. Anytime it's horizontal, it's a slope of 0. Look at that, how convenient, it's right at the maximum. So if you make your slope equal to 0, your first derivative equal to 0, you can find the value of x, which gives you, which reaches the maximum, right? So if you solve this, finding a value for x, you will find that you end up with 8.773. See? If you're not sure how to solve this from this step because you have x squared on this side, there's a couple ways you can do it. See? I'm going to show you the classical one. So you want to get x squared alone, all right? So first things first, I don't like that there's a negative with the x, so I'm actually going to do plus 27 divided by 4 x squared to both sides. So I have this on the left side. On the right side, I have just this. I want to keep getting x alone, so I'm going to start by multiplying by 4 to both sides. So I end up with 27 x squared equals 300 times 4 times square root of 3. Divide both sides by 27 to keep getting x alone. I'm running out of space, but I think I can do it over here. So we have x squared equals 300 times 4 times square root of 3 divided by 27. And to finish getting x alone, I'm going to do x equals square root of that whole thing. Now I know that some of these values I could have simplified them before, for example 300 times 4, but what matters to me much more is the process. See, so I get x alone, I do the square root to both sides in order to get rid of the exponent, and we end up with something that looks a little nasty, but it'll give us the answer because we followed the method. If you follow the method, you will always get there. So 300 times 4 times square root of 3 divided by 27. Boom, 8.7738, which is the same 8.773 from up here. So I just want to show like the sort of classical way to solve it, but hey, both work. See, if you ever have to find the minimum, this is no different. Okay, at the minimum, if you look at the slopes, see, this has a slope of negative, I don't know, 3. This has a slope of negative 1, and this has a slope of 0. So that right there, at either max or min, you will always have that your derivative, in this case dv dx, has to equal 0. So yeah, rule of thumb, if you have the slope equal to 0, you're going to find the x value of your max or minimum. Awesome. So that is for part E. For part F, hence or otherwise, find the maximum possible volume of the box. Here it has to do more with like the context of the problem, and so the context of the problem for x is going to be, it has to do part of like a distance. See, x is part of a distance in this scenario, and your y value is going to be volume. See, why is your y value equal to volume? Because this v on the left side is usually going to be y. See, what is your y in this case? It is this guy here. Let me use a more vibrant color. So this 3039 is the volume when x is 8.773. And when x is 8.773, we are talking about the maximum. So at the maximum, in other words, the maximum amount of volume is going to be 3039. So actually, for part V, we sort of already solved it. For part F, you're going to have that it's 39.34 centimeters cubed because volume. If you want to be consistent with significant figures or whatever, you can go like this. So that is for part F. Technically, we already did it before, but hey, context matters. Interpreting your results matters as well. See, so whatever your x value is the maximum, that also makes reference to the maximum of your volume. See, down here we have x values from 0 to 16. Up here from 0 to 3500, we have our volumes. Bada bing, bada boom. There we go. Lastly, we have that the box will contain spherical chocolates, and the production manager assumes that they can calculate the exact number of chocolates in each box by dividing the volume of the box by the volume of a single chocolate and then rounding down to the nearest integer. All right, you might want to read that twice. All right, but point is, um, this is one of those sort of questions that you can answer like theoretically or with words. All right, and so what are a couple things that our manager is doing wrong? Well, the first of all is that here it says that the manager assumes, so this guy's assuming, so that is already like a small mistake, that they can calculate the exact number of chocolates. And so if you're doing an assumption and you think that's going to give you an exact value, you're a little bit wrong. See, it's going to be like a little bit off. See, so that is already one way to answer. And you, so yeah, I'm just going to write that for now. So one way that he's wrong is that the values aren't mega exact. There is wasted space. All right. And also, you can say that the model that we worked on, see, uses, and this is straight from the answer key actually, uses external values. So in other words, like volume has more to do with what's inside, while surface area, which is what it started from part B, has a lot to do with what happens outside. See, so we worked with area of the base outside, stuff like that. It's not as consistent. See, it would not be wise. You can look at the answer key, but anyways, I'll pull it up now just so you take a moment and read it. But really for part for part G, you can't just kind of like talk about it. See? So wasted space or spheres do not pack densely, which is basically like um, they don't pack like water. There's always going to be a little bit of gap of air between them. Or as I said, the model uses exterior values, stuff like that, etc. You don't know how thick the packet of the chocolate is either. Point is, this is worth 1 point, dude. And there's a lot of different things you can say. So you do not have to say all of these 4 things to get 1 point. As long as you say 1 out of 4, you're good to go. So that's also why at this point in time, I kind of just like spit ideas. And hey, whichever one you remember the most is probably going to be the most useful one. What I like to do for these exercises is really take a good read at what it's saying, and you will always find something that's like a little wrong. So first of all, as I said, the manager is assuming, and he thinks that he can get an exact number of chocolates. So exact is a strong assumption. There's got to be something a little bit off. Probably some space in between is what makes more sense to me. So that is why the manager is incorrect. There's lots of reasons. That's my favorite one. That is how you solve paper 2, specifically number 5. I hope it helped. Take it easy. Hey man, we'll see you around. Peace.